Osmotic pressure. In this video, we will define/review osmosis. We will then define osmotic pressure and use the principles of osmotic pressure to learn things about the solution. In our case, in this video, we will use it to calculate the molar mass of a solute. Though as with all of our example problems, focus on the problem-solving concepts rather than the exact problem, since there are many similar problems that you should be able to do and will practice in the homework. This problem will actually be one of the most complex I give you for colligative properties in terms of example problems, and that's just because this is the last one introduced, and so I think that you're ready for a little bit more complex problem solving. So first, a bit of review about what osmosis is. Osmosis occurs when a solvent flows from a low concentration of solute to a higher concentration of solute. This can happen when two solutions are separated by a semipermeable membrane that allows the flow of water, but not the solute. You may remember this from your bio classes, either in college or high school, since this is a very important principle in many biological systems. Osmotic pressure is defined as the amount of pressure that would be required to push a pure solvent to prevent it from passing through a membrane into a solution. The more concentrated a solute is, the more osmotic pressure. We can visualize this by looking at a tube separated by the semipermeable membrane in the middle. On one side is pure water, on the other is a solution. The water will push through the membrane into the solution until the force of gravity pulling on the solution is as great as the osmotic pressure. If you increase the amount of solute in that solution, it would go up even higher because it would take more force, more gravity, to be able to prevent that from happening. Now let's look at this a bit more quantitatively. We know that in osmosis, the solvent flows from a high solute concentration side, but we can quantify this by using osmotic pressure, denoted by a capital Pi, is equal to the molarity times the ideal gas constant times by T. Here, because we are not changing temperatures, we are at a constant temperature, we are able to go back to using molarity rather than using molality. I didn't really discuss it, but the reason for using molality for the temperature changes just has to do with the fact that you are changing temperatures, which changes density. As with all other colligative properties, you must consider the Van 't Hoff factor when calculating the concentration. I won't discuss that again here, but make sure you factor it into your calculations. So let's do an example problem. This is a bit of a fun problem. Instead of simply calculating the pressure or the concentration like we've done for all the other ones, I'm going to ask you to calculate the molar mass. As with the problems, focus on the problem-solving techniques rather than each specific step, and know that you could do similar sorts of problems for all of the other colligative properties as well. Let's first look at the problem. I give you the mass of a protein used and tell you the volume of the solution, as well as the osmotic pressure. If we organize all of our information and all of our equations, we can start to get some idea of what to do. We have everything in the osmotic pressure formula except for the molarity. And furthermore, we even have the volume, not just the moles. And so if we fill everything into that formula, we can then calculate the moles. If we have moles, we can compare that to the mass given, because we know that molar mass is grams over moles. So let's do that. Doing this out, we can convert the osmotic pressure into torr, and then fill in R and T. We also know the volume, and so for molarity, we can fill in the unknown moles over the 0.0100 liters, which leaves us our moles as unknown, and we can solve for that. Note that we had to change this into atmospheres, even though we didn't in some of our earlier examples when we were doing colligative properties, because we're using R. R has atmospheres in it, and so we need to use atmospheres as our pressure. Since we are trying to find molar mass, if we have moles, which we found, and we have grams, which was given, we can simply put grams over top of moles to get our answer. And we get 3,526. Now this might seem really big. I know you're not used to dealing with molar masses quite this large, but proteins are generally very large compared to what you've been used to dealing with. This is actually a relatively small protein, so don't be concerned about the molar mass going into thousands or even tens of thousands if I mention that it's a protein that you're calculating. In review, Osmosis is the flow of a solvent from areas of low solute concentrations to areas of high solute concentrations. Osmotic pressure is defined as the amount of pressure that would be required to push on a pure solvent to prevent it from passing through a membrane into a solution. Mathematically, this is osmotic pressure, or capital Pi, is equal to the molarity times by the ideal gas constant times by T.